Okay, hello everybody. Am I coming in loud and clear? Can you let me know in that chat button? Good morning, Alan. Elena, hello. It's nice to be back. Jun Sheng, hello. Glad you could join us. Hello, Abdulaziz. So I asked everybody in the who's here, what did you do in week 6? Most people, the highest response is sleeping. It's good to know some people took a holiday and some people studied twice as hard. Also, some people probably learnt weeks 1 to 5 in week 6. If you did, good job. Alan, yeah, the time is flying. The time is flying. So it's crazy, right? Anyway, I missed you all last week. I do hope you had a good week. Just remember that the writing assignment is open. So let me know how you're going with the writing assignment in the chat if you get a chance, okay? So today we're going to continue our odyssey into algebra. Oh no, calculus. This is calculus, right? Sometimes I forget what I'm teaching. And today we're going to look at polar coordinates. Yep, yeah, penguin today, Eleanor. Yes. Oh, don't worry, Gion Hui. There's still plenty of time. There's still plenty of time. Okay, so in today's lecture, we're going to look at polar coordinates. Now, polar coordinates are familiar because you've already seen them in complex numbers, right? So essentially you have a point in the xy plane, let's say, and you've got an angle to the positive x-axis and a length to the origin. Okay, so this stuff is similar to your work with complex numbers. Okay, so in particular, the polar form, right? So the polar form. Okay, so the polar form for complex numbers involves the same thing, an angle and a length. Okay, so I think this should be a pretty easy lecture, the most difficult thing is probably when you want to sketch or plot polar curves. That's probably the most difficult thing, but you do have Maple to help you out, and so I'll show you a little bit involving this. We'll also do some calculus, right? So let's get started. So the idea is to consider, say, 2 points. A point, right? And that's a point P, let's say, and it'll have some distance to the origin, which we're going to denote by R, and it will have some angle to the positive x-axis. Okay, so the point P depends on the distance to the origin and the angle. And similar to what you did with complex numbers, along here, theta is 0, and as you rotate anti-clockwise or counterclockwise, the theta increases. Okay, so why is this interesting? Why would you want to know what to do it? How to use this? Well, it's an interesting framework that helps with things like spirals and other round phenomena. So I'll give you an example in a second. Okay. All right, actually, I can do that now. So let's say I have R as a function of theta, okay? So as you rotate, the distance to the origin changes. Let's take a really simple example. R equals 2 theta. Okay, so what that says then is that as theta increases, the distance to the origin also increases. Okay, so if I draw a little curve here, when theta equals 0, r equals 0. When theta equals pi, so the angle is there, this will equal pi on 2, this will equal pi, so you sort of go up there. And then as you rotate, you keep getting bigger and bigger and further away from the origin. Okay, so this is an example of, of a spiral. Okay. Now, if I wanted to, say, sketch these things with some software, what I can do is, let me just bring that up. Yep. I can use the plots calling sequence. So I put in with plots, and this is the one you want, the polar plot. Okay, so polar plot, the command, you've got r as a function of theta. Here I've put in r equals 2 theta. And if I just do that, you can see, well, here it is. It's spinning around and around and around, right? Okay. And I've gone for theta between 6 and 0 and 6 pi. Down here, here's another one. This is r equals the absolute value of cos 2 theta. And so you can see here, we've got this nice symmetry. It looks like a 4-leafed clover. Oh, how beautiful. Okay. So there are some ways of plotting these things. Now, I'll also show you how to do it by hand, but this is probably the most confusing thing out of all the stuff with polar coordinates and whatnot. Okay, so before we get to plotting, let's look at some basic relationships here. Again, I would hope that these would be quite familiar to you. So you can just use Pythagoras and trig to come up with these formula. Okay, so basically you've got, let's say you've got a point here. That's your point P. What you can do is, let's draw a right angled triangle. Okay, there's your angle. There's the length of your hypotenuse. Okay. And so this will be sort of your x point, this will be your y point. So you can just relate them using Pythagoras' theorem and basic trig. Okay, nothing too difficult there. Okay, well, usually, well, we will in this course, we're always going to assume that r is not negative. Okay, we're not going to talk about negative distances or anything like that. And the theta is allowed to roam free. Okay, usually. Okay, so this is important. This is sort of less important. We can manage that. All right, so let's do some examples and see how it all works together. So we'll start small, just with points, and then we can move on to curves and stuff like this. All right, for the following points given in polar coordinates, sketch them and convert them to Cartesian. Okay, so I can do the first one. That's pretty easy. So the distance is 2 units away, and the angle to the positive x-axis is pi on 3. So I guess it'll be somewhere up like that. Okay, that'll be pi on 3. And that distance will be 2. Okay, so it's lying in the first quadrant. The angle is pi on 3, and the distance to the origin is 2. Now, if we want to convert them to Cartesian form, well, you can use basic trig, or you can just use these formula here, or you might just be able to see it straight up. Okay, so let's just do it the longer way. So x is going to be 2 cos pi on 3, and cos pi on 3 is a half. Okay, so if I draw a little line down here, the x component will be 1, and the y component is going to be 2 sine pi on 3. Okay, and sine pi on 3 is root 3 on 2. So that's just going to be root 3. Okay, so the x component for this is 1. The y component is going to be root 3. Okay, so this is in polars. This is in Cartesian. Okay. Now, for these kind of problems, what you really need to remember if you want to do it by hand are the simple triangles that let you work with trig, the basic trig angles, right? So that's one of them, and the other one is here, right? Both of these angles are pi on 4. If you can remember them or draw them, derive them, then these things are usually pretty easy to work out. Okay. Sometimes it's not one of these standard angles, but most of the time it is. Okay, so for this one, let's have a look at where this one is going. This is 5 units away from the origin, and it's negative pi on 4. So instead of rotating this way, anti-clockwise, we'll rotate the opposite way. Okay, so this will be something like this, and that'll be 5. Okay, the distance. So you know that here the x component's going to be positive, the y component's definitely going to be negative. Okay, so let's work that out. Okay, so cos is positive in this quadrant, so it's just going to be 5 cos pi on 4, which is 5 times 1 on root 2. Okay, and the y component is going to be negative. Okay, so it'll be 5 sine negative pi on 4. Okay, you know it's negative, so it'll be 5 times negative 1 on root 2. Okay, for this one, you know it's just going to be, so that'll be point A, point B, and point C will be 2 units away, and you want to go all the way over here. Okay, so if you just repeat that process, C, so that's 2 and that's 3 pi on 4. C is going to be something like, what have we got? Negative root 2, root 2. Okay, I won't do all the things because I've run out of space there. But you can kind of see a pattern here. You just use trigonometry to knock these over. And I always like drawing a picture, right? Like they ask you to sketch them here. But if you can draw a picture, then you have a better idea of what's going on with the location or the placement of the point. Okay. All right. So now let's go the other way. These are in Cartesian coordinates, and we want to convert them to polar form. Okay, let's do F and G first because they're pretty easy. E is a little bit harder, so let's actually do F and G first. Okay, so who can tell me in the chat what will be R and theta for F? What will be R and theta? Who can tell me in the chat? There are 50 people here. Yep, Abdul Rahman, that's the Cartesian form. We want to convert to polar. So Bojia says it's 1 unit away, correct, from the origin. What about the angle? Who can tell me the angle? What's theta going to be? Who can tell me on the chat? Yeah, it's going to be pi, correct. Okay, so you come around there and you go all the way out there. All right, so that's an easy one. So in polars, f is going to be 1 pi. Okay, what about g? Well, let's draw it. So it's -2, -2. So it's sort of maybe, oh, -2. So it's down there. So who can tell me, this is G, what is R and theta going to be for this one? Who can tell me on that chat? Smash that chat button. Yes, excellent, excellent work, people. I'm loving it. That's going to be 3 pi on 4, and we're going in the clockwise direction, and that's going to be square root of 8, or 2 root 2. Okay, so G is going to be square root of 8, or 2 root 2, and -3 pi on 4. Okay, excellent. Thank you, Russell and Eloisa and Zhonghua. Now, E is a little bit more complicated, so let's draw that. So it might be there. And the challenge with this one is that it's not a standard angle, okay? So it's easy to get the length because you can just use Pythagoras, but the angle is not so great here. So let's work it out. So it's going to be √3, yeah? And the angle is given by y over x, which is 1 on √2. Now, this isn't a standard thing, so theta is approximately equal to 0.615 radians. Okay, so in this case, R would be √3.615. Now, usually, just like with complex numbers, we work in radians here. It's always good to work in radians. Okay, so nothing too difficult about these. They're sort of entry level, and they should remind you of what you've been doing with complex numbers. Okay, so nothing too crazy there. Russell, I'm leaving that as an exercise for you, Russell. So see if you can work it out. Okay, yeah, see if you can work it out. All right, so you just repeat what's going on here, and you know, in this quadrant, sine is positive, so x is going to be negative, y is going to be positive, so you know the signs when you do, you know, cosine and sine and that sort of stuff. All right, let's move on to something a little bit more challenging. Sketch the graphs of r equals 4 and theta equals pi on 3. So now we're getting into something a bit more difficult. And the way I like to look at these problems is actually visually. You can do them algebraically, but I wouldn't really recommend that all the time. So let's have a look, and we can sort of work through it together. So r equals 4. Okay. All right. So that, and I'm not told what theta is in this case, right? So basically, you know, how can I work this out? Well, so I want to be at 4 units away from the origin. So I can, if I want to, I can go like this and then square both sides. And so this looks familiar now, right? This is a circle with radius 4 and center at the origin. Okay, so if I was drawing this, I would recognize that, well, this is really telling us that I want all those points that are exactly 4 units away from the origin. Okay, so that's your set of points. All right. Absolutely, Abdul Rahman. It's a circle. It's my poor attempt at a circle. Okay. But what about this? What do you think? Okay, let's go to the chat here, people. What do you think this is going to look like? This is a circle. What is that going to look like? Well, you're close, Abdul Rahman. I think you're very close. Anyone else want to have a guess? There's 49 people here. So you're almost right there, Abdul Rahman. Oh, Nicholas, good guess, but not correct. But thank you for suggesting that. What we want is all those points. Oh, CZ Chan, you legend. It's a half line, right? We want all those points that are that when you make the angle with the positive x-axis, it's pi on 3. Okay? So this is like a ray, called a ray or a half line, as CZ Chan said. Okay? Great question. So these are real simple things. Again, we're going to look at more difficult and challenging things, but we need to sort of understand what the simple curves are before we move on to the more difficult ones. Okay, so let's level up and see if we can talk about these sort of questions. These sort of questions are very common in this course. Okay, you know, I'll actually just see if I can pull up Maple or something first. Let me just have a look. So just bear with me for a second. Yeah, I'll just put it in now. So just give me a second, everyone. So the question is, how do I draw this? It's easy to do it if you've got computing, but let me just share with you what this looks like. Okay. Look at that crazy curve. Obviously, it's not a function in terms of y equals f of x, but look at that. Does anybody know what its name is? It's got a special name. Looks a bit like an orange. Looks a bit like an apple. Yes, absolutely, Abdul Rahman. Looks a bit like a cardioid. So it's supposed to look like a heart, a bit like a heart. And if you change the curve, you can get a really strong heart. Yeah, nice, Aiden. Okay, so how do I do this? Well, one strategy here is to draw the curve in the xy plane first. Okay, right? So this is the curve 1 minus sine theta, or 1 minus sine x, where the horizontal axis is the theta axis and the vertical axis is the function axis, right? So you start with sine x, you flip it to get negative sine x, and you move it up 1. That's how I would do it, right? And so the question is, how do you go from this to this? Okay, so that's the question. All right, so let me work through that, because it's a little bit tedious, but I think it's important to know. So let me just show you how it works. All right, so I'm going to firstly sketch the graph of 1 minus sine theta. Okay, so I'll go up there, that'll be 2, that'll be 1, and it's going to look something like this. Okay. I don't want all of this curve. This this is your pi on 2. This is your pi. This is your 3 pi on 2, and that's going to be your 2 pi. So, because I don't really need this bit here. Okay, and I've got that, so this is really an open curve there. Okay, so what one strategy is to draw these is to say, okay, as you vary theta, what happens to r, and then draw that in the curve below. Okay, so now I've got this going on with my polar curve. You can see when theta equals 0, r is already equal to 1. So I would start at 1 on the positive x-axis. And as I rotate, I want to see, okay, well, the distance decreases down to 0. So by the time I've done a quarter of a rotation, I should be back at the origin. Then it extends again as I keep going from here to here, right? And then it extends even more as I go from here to here. And then it decreases from here to here. Okay? So at this point, it should be sort of -2. Right? At this point, it should be -1. And so what happens is, look, something like that. Okay? So the difficult thing is moving from this information to this information. Okay? So it's a skill that's best learned through, obviously, through practice. Okay? I mean, this is a nice smooth curve, except for that point there. Okay, so I'll do a couple more examples, but the more of these examples you can do, the better. Okay, now obviously you're going to have Maple and stuff to help you in the exam. So you know, this is important to know, but you will have some technology available to you, obviously, right? Let's do another one. I'm going to do. I'll go back up to Maple now. Let me just show you another one. Okay. So here is Maple. So I've used polar plot, absolute value of cosine 2 theta. Okay. And you can see, well, that's a lovely little looking curve there, looking like a 4-leafed clover or a flower or something like that. Oh, how nice. Okay, so that's sort of, we know what we should end up with there, and there's some nice symmetry there. Okay, but you would start out here, as theta increases, you get back to 0, then it goes out and increases, decreases, increases, decreases, increases, decreases, increases. Okay, so how do we represent that? Oh, Abdul Rahman, thank you. That's so cute. Let me have a look at the next one. So that's that, which I've just shown you in Maple. So if I was doing this by hand, what I would do is I would firstly sketch the graph of cosine 2 theta, and then sketch the graph of absolute cosine of theta. So 0 to pi. Okay, it's a bad graph, but you get the idea, right? So this will be cosine 2 theta. And because you've got a 2 theta here, you squish the intercepts, right? And all the things. So this would normally be pi on 2, but because there's a 2 theta, you divide, right? Okay, and you sort of end up at 2 pi. All right, so to get this curve, you flip everything. Okay, so it will be something like this. Right? So that'll be pi on 4, pi on 2, 3 pi on 4, pi, etc., right? And then bam, up there. Okay. So now this is cosine 2 theta absolute. All right, cool. So once we've got that, what we would like to do is move this very dodgy sketch over to the polar form, right? So, okay, so when theta equals 0, r equals 1. So we know we've got to start out there. And then what happens is as theta increases, the distance decreases back to 0. So looks like that. And then between here and there, it goes back out. Okay? And then comes back down again. Yeah. And you just keep going. Ah, how nice. I know. Feel the love, people. Feel the love. All right. So you can say, hey, honey, I got you a flower, and here it is. It's absolute cos 2 theta. All right. So the key with drawing these polar plots, firstly, you've got Maple to help you, okay? Secondly, if you draw them with on the theta r axes and then transfer them over, okay? And always ask yourself, as theta increases, what is r doing? Okay, now that you can do symmetry and all that sort of stuff, but mine are just pretty simple explanations, okay? All right, so let's talk about some calculus. A lot of functions here and curve sketching and all that sort of stuff. Let's actually do some calculus, people. All right. All right, so we're going to look at derivatives of polar functions now. So you've got r as a function of theta. Okay, so it might be something like, I don't know, r equals 2 theta, r equals sine 3 theta, r equals 1 plus cos theta. They're all examples of where r equals a function of theta. R depends on the angle theta, right? And so what we're going to do is try to understand how do we sort of differentiate this sort of polar function. So if you look at the derivative, then we can sort of write it either way, right? dr d theta or f dash of theta. They're both fine. Okay. So if r is a function of theta, then you get this giant mess here. Now, I'll show you how to derive it because I've got time, but the idea is to really ensure that you've got all the x and y components just depending on theta, and then you can just differentiate. I'll show you how to do that in a minute. So that's a dash. I think in your book, in the course notes, this is the format that they have, but this is okay. It's nice and compact. Okay. All right. So where does this crazy formula come from, and how do you use it? Well, I'm glad you asked. Okay, I'm glad you asked. product chain rule. Okay, so let me just show you how it works. Okay, so we know that in polar coordinates, x equals r cosine theta. That's the relationship between Cartesian and polar. And y equals r sine theta. Now, if this r is a function of theta, we can write both of these things like this. So notice x only depends on theta now, and y only depends on theta. Okay? So what I can do is differentiate these using the product rule. Okay? And the chain rule. So we want dy dx. By the chain rule, it's just this mess here. And you know dy d theta can be computed from this, and dx d theta can be computed from this. Okay, so what is dy d theta? Well, we don't know what f is, but we can differentiate this using the product rule. So here I've used the product rule for differentiation. And the same with the bottom, dx d theta. Well, if I differentiate this, I'll get have I made a mistake there? Hang on. Oh yeah, cos goes to negative sine, right? Oh, almost made a mistake. Whew. Okay, so that's where it comes from. And the question is, how do we use it? Well, I am glad you asked. I am glad you asked. So a standard kind of question here would be something like the following. You've got a function of theta, r equals a function of theta, compute the derivative dy dx, and then what is it at certain points? Okay, so before we do that question, let's actually draw a picture and we can try to work this out without even doing any math whatsoever. Okay, so that's our function there. Our function is going to be 2 sine theta. So let's see if we can wake up everybody, and I'll see what I can do. Okay, all right. So let me go over to GeoGebra, and you can play along with me. All right, here it is. This is the curve r equals 2 sine theta. Okay, you can see it's a circle with radius 1 unit and center here. Okay, who can tell me what is the derivative when theta equals pi on 2? What is the derivative, just from the graph, what is the derivative when theta equals pi on 2? Advaita. Gosh, you didn't lose any time answering that question. So why is it 0? You're absolutely correct. Why is it 0? So you're right, and thank you for your chat. So why is it 0? Who can tell me? Come on, there's 48 people here. Why is it 0? I've forgotten. I can't remember. Who can tell me? Come on, 48 brilliant minds. Yeah, exactly. The slope of the tangent line up here is just a horizontal line, right? Okay, so you're absolutely correct. Advaita, you're absolutely correct. Now, what about us? What about at theta equals pi on 4? Oh, theta. Who can tell me what is the slope of the curve at theta equals pi on 4? Who can tell me? Eric says 1. Thank you, Eric. Abdul Rahman says -1. Who can tell me? No one's got it yet. Undefined. So if I go here up to sort of an angle of pi on 4, you can see that the slope is going to be an infinite slope, right? So it won't be defined. So without even doing any maths, we could really just work that out pretty easily, okay? So that's why I like drawing pictures. And yeah, let's complete the question. Okay, all right. So what do we need? Well, we want to compute the derivative, so let's use this. So let's compute f dash dr d theta. So that's going to be 2 cosine theta. Okay, and so we can just now, if we want to, put that into this thing. Or this. I might just use this because it's a bit easier. Okay, so r is that. So I'll get 2 sine theta cosine theta plus that times sine theta. See if I can squish that in. And down the bottom, I'm going to get negative r times sine theta. So that's going to be -2 sine squared theta plus 2 cos theta times cos theta. Okay, so obviously I can simplify that up the top. Okay, so let's see if our calculus work here actually matches what we've been seeing from the graph. Okay, so at theta equals pi on 2, well, when theta equals pi on 2, cosine theta is going to be 0. Yeah, because that part will disappear and this is non-zero. And at theta equals pi on 4, what happens is sine theta equals cosine theta equals 1 on root 2. This will become 0. Okay. All right. So this was the bulk of the work. This was pretty easy. We also had a look at the pictures before we did the calculus, because sometimes you can tell a lot by just looking at the pictures. All right, people, we have got about 5 minutes. So What do you want to talk about? Do you have questions about the writing assignment? Is there anything you'd like me to talk about um, in particular? Like you want me to talk about extra details or another example, or let me know what's going through your head. Obviously, it's a bit hard because you have the algebra and then an hour of calculus. So let me know what is going through your minds if you want me to chat. Everyone can turn their microphones or videos on. Slide 7. All right. So there's 7 again, Abdulaziz. Let me get to that in a second. Yes, Maximilian, there is a certain structure of writing, and you can see the five criteria on the Moodle page. Okay, so whenever I try to give feedback to students, it's all the first thing you want to do is check your work against the Moodle page criteria. Let me see if I can just find it now. Here we go. So I'll just, yeah, that's it. And yeah, this is the most important thing. Let me just go back here. Thank you, Russell. I'll just go over to the other page. So Maximilian, you can see here, let me just make that bigger. Marking rubric is the ideas that your assignment will be assessed on, right? So is the work written in sentences and paragraphs with correct grammar? Is the explanation okay? Is it self-contained without reference to the question? Is it correct? And are you using a math editor to do equations properly? Okay. All right, Abdulaziz. So what's going on here? Let me just go back and share again, because it's a hard problem, right? So with this one, you want to transfer this information over to this, right? So the vertical axis is the distance to the origin, and the horizontal axis is the amount of rotation. So you can see, hopefully, that when on this graph, when theta equals 0, I'm 1 unit away from the origin. And as theta increases, the distance decreases. So as I rotate this way, the distance decreases. Okay, so let's say, I don't know, this distance is going to be greater than this distance, right? And again, then as I go past this angle here and to the next quadrant, the distance to the origin is increasing back from 0 to 1 again. And then when I get to this part, I've already done a half rotation. I want to do another one. It's increasing even further up towards 2. And then it comes back down again. Okay. So that's pretty much how you transfer these diagrams over to these diagrams. Just think about, well, what distances am I away and what is theta doing? All right, so Aidan, do we need to copy questions to an answer sheet? Yes. And what some people do is, okay, like top tip in the last minute, don't take screenshots and paste them into your document. It won't work, okay? It will not work. Type them. You've got to type everything pretty much, right? Yeah, Louisa, I agree. It is easier, but like what I think what the school wants you to do is to read the marking criteria and implement it in your own way, in your own style. Okay, because what happens is, I think if you had a sample, people just copy the sample exactly. You know what I mean? That's not what we want. I think that's the most important thing. But you know, maybe I can have a session on the writing assignment. Maybe we can do a tutorial or something. No, diagrams is fine, Maximilian. Yes, diagrams is fine to do screenshotting, but text and equations are not. Okay. All right, folks, I've got a tutorial at in about 1 hour. So maybe I'll see some of you there. If not, welcome back to week 7. It's been great. Happy to be back with you again. And I'll see you later this week. Yeah, just enjoy being back. And thanks again, everyone. All right. Fluffy's back. This is Fluffy the penguin. Yeah, Fluffy. All right. Thanks, everybody. Bye.